So in this video, I will be solving part 1 of the homework here, where we have a sealed cylindrical tank with height h, big H, and cross-sectional area of AC, and it's filled to height hi with water. The headspace above the water is initially at 101,325 pascals, and a hole of size 0.001 meters squared is punctured at the bottom of this cylindrical tank, and the water starts to drain out. So our task is to derive a differential equation for solving the height of water in the tank as a function of time. So as you can see, I have a diagram here of this situation. We have the cylindrical tank, height of big H, and cross-sectional area of AC. And then we have this liquid here at height hi, and the pressure above the liquid of 101,325 pascals. And as you can see, here's the little punctured hole that the water is spewing out of. And our task is going to be, as I said, to find the height of the liquid as a function of time as it is flowing out. So I'm just going to represent that here by h, like that. So how we're going to want to start this is we're going to want to get the number of moles first up here of the gas above the liquid. So we are going to use our ideal gas law, PV equals N RT, and that pressure is going to be P naught and V naught, and it's still going to equal nRT. So then we can get that N is equal to P naught V naught over RT. And now we can plug in our P naught. So M will equal 101,325 pascals. And then our volume here is just going to be H minus HI, to get this length here, times the cross-sectional area. So H, big H minus HI times cross-sectional area. All that is still over RT. And now we're going to want to try to find the pressure when we're at any height h of the liquid. So for that, we're just going to call it P1 and V1 equal to N RT. And again, we're going to want to isolate P1 equal N RT over V1. And now what we can do is we can plug in what we got for N, and we can plug in what our new volume will be, which will just be big H minus little h times our cross-sectional area. So that'll end up being, again, 101,325 pascals. H minus H. I times AC, and then we still have that RT from this equation up here. And then that'll be all over. We have our RT from our N over here. RT. And then times our new volume, which again is big H minus little h times our cross-sectional area. Minus little h times our cross-sectional area. So as you can see, these cross-sectional areas will cancel, these RTs will cancel, and we'll end up that, I'll write it down here, our pressure of the gas above the liquid at any height of the liquid is equal to 101,325 pascals times big H minus HI all over big H minus little h. And that will again be the pressure for any height for the gas at any height at which the liquid is at. So now what we're going to want to find is the velocity of the liquid going out of this hole right here. So how we're going to do that is we're going to use Bernoulli's equation, which I've written up here. P2 minus P1 over rho plus V2 squared minus V1 squared over 2 plus G times Z2 minus Z1, and it's all equal to 0. So the first thing that you can notice is that our V1 is actually basically going to be 0, and that is because our V2 right here is coming out of that little cross-sectional area, so it would be a really, really, really large number. And our V1 is at this huge cross-sectional area, so it would be a really, really small number. And a really, really small number squared is basically going to be 0. So I'm going to start recopying this down. Over rho plus V2 squared over 2 plus. So our Z2 minus Z1 is actually going to end up being just negative h, because our Z2 down here is just going to be 0, and then minus our Z1, which will be the height of our liquid h. So it'll end up being 0 minus h, which is just negative h. So it'll be minus GH. And now we're going to want to get this V2 on its own side. We're going to add GH and subtract this on both sides. So we'll get V2 squared over 2 equals GH. I'm actually going to flip these in order to keep this positive. So plus P1 minus P2 all over rho. And now all we need to do is plug something in for P1 and P2. We already have our P1 equation. So now we just need to think about what our P2 will be. And that pressure, once all this is exited, is actually just going to be atmospheric pressure, right? So it is going to be 101,325 pascals. And now we can plug both of these in. Again, this left side will be the same. P1 equation 101,325 minus HI H minus H, and then minus 101, 3, 2, 5, all of that over rho. And now you can see we can factor out a 101, 3, 2, 5 and a rho from both of these. So we'll get V2 squared over 2 is equal to GH plus 101, 3, 2, 5 over rho and then times our H minus HI over big H minus H, and then just minus 1. And now finally, to get V2 isolated, we multiply by 2 on both sides, and we get 2, and then this here, G H plus 101, 3, 2, 5 over rho times big H minus HI over big H minus little h, and then all that minus 1. And then all this will be square rooted as well. And that will be the velocity equation. So now that we have our velocity equation, we now need to relate that to time somehow. So how we're going to do that is we're going to use the volumetric flow rate coming out, which will be Q, so used to writing a row, Q out right here, which will be equal to V2 times A2. And we also know that Q out will be equal to the change in volume over change in time. And that change in volume is actually going to just be our cross-sectional area times our change in height. So we can say that Q out, negative Q out is going to be equal to the cross-sectional area times the change in height. And now we can set those equal to each other. So AC dH over dt is equal to negative V2 A2. So now we can divide AC, and I'm actually just going to start calling that A1 to make it simpler, more simple. So we're going to say negative V2 A2 over A1. And now what we can do is we can plug in our V2 equation. We'll solve for it right here. So we'll say that dH over dt is equal to, I'm just going to have A2 and A1 out in front, and then our V2 equation. Square root 2 GH plus 101, 3, 2, 5 over rho this time. H minus HI over H minus little h minus 1. And all that is square rooted. So now this is going to be the differential equation that we will be solving in the coding part of this video, which we will start now. So now we will start our coding part of this video, where we will be solving this differential equation right here and plotting our answers as well. So to start off, I've already put in some of the imports that we need for this code. And the first one right here is importing numpy as np, and that is numerical Python. And basically it is used for a lot of mathematical functions, and we will need it for the square root function. And then I've imported solve IVP from SciPy integrate, and that is going to be how we will be solving this differential equation. And then I've imported the subplots from plotly.subplots, and that is how we will eventually be plotting our answer. So to start off, we're just going to put in some of the values that we know from our problem. So the first one is big H is 1 meter. And as you can see, I've put the units after a hashtag symbol, and that basically makes it a comment so it won't impact our code. We have the cross-sectional area of AC is equal to 1 meter squared. But again, in our problem, we just called that A1, so I'm going to call it A1. Again, that was 1 meter squared. Correct? Yes. And then we have it filled up to height HI of 0.9 meters of water. So HI will equal 0.9 meters. And then A whole will be 0.001. And again, for us, that's just going to be A2. I'm going to label that as A2 will equal 0.001. And that should be meters squared, yes. Meters squared equals, and we will also need our gravitational constant, 9.81, and then we will also need rho, our density, which will be 1,000. So now we're going to want to define a function that we are eventually going to use the solve IVP on. So I'm going to define a function, and I'm going to call it the right-hand side of this here. And we're going to have two variables, time and height, which will be represented by y. And that is because we are solving for the time with respect to the height decreasing, or the height is decreasing with respect to time. So again, this height is going to equal an array y value, so we can eventually use the solve IVP function that can only be used on an array. And we will only have one value in this, so that's why we will have the 0 index here, since Python starts at an index of 0. And then now what we can do is we will type in this function here, which we will call dHdt, and it will equal negative var a2 over a1 and that times the square root, which again is going to be np dot square root, yes. And it will be a square root of this whole thing here. So we will have 2 I'm going to put the 2 here, 2 times, and then this whole function here, g times h plus (101,325) over rho put parentheses around this. And that 101,325 over rho is going to be multiplied by big H minus HI over big H minus H. This one. Okay, so again, let's make sure this is all right. So a1, negative a2 over a1 times okay, so we are missing some parentheses here. There we go. So numpy square root. Again, it should be of that whole thing. Yes. 2 times that whole thing. G times H plus this whole thing 101,325 over row times this whole thing. That whole thing minus 1. Yeah, so this should be correct. And then we want to return dh dt. And that should be good. So now we're going to want to use the solve IVP function. So solve IVP. And first we have to give it the function that we're solving, which again is the right hand side that we just defined above. And then we have to give it a starting time, which is going to be t equals 0. And then final time, which we're just going to go with 10 to start and see if we need to change it. And then we have to give it the initial height, hi. And then the method, which we'll be using redo, and then the dense output will be true. And I'm just going to run all. And we did get an error here. Oh, so as you can see here, again, we made this a array with one index. So that means our answer down here also has to be an array. So if we put brackets around this and run this, then this should run. And now what it says is that the array must not contain infinites or NaNs. And basically what that means is in some time here between 0 and 10, this will be negative, and it is trying to take a square root of a negative, which it cannot. So maybe we can try a different number like 2 and see if it'll run. And yes, it will. So as you can see here, this basically means at 2, the height will be 0.89, whatever. At 0, again, it's the 0.9. And at 0.215, it'll be 0.899 as well. So one solution that we could use to help us when we are going from 0 to 10 is we could just put an absolute value inside the square root. So then all those are just positive. So I'm going to put numpy absolute value. Around everything in the square root. And run that. And run this again, and as you can see, now we get some values for our 0 to 10. But again, these will not be the exact values that we will want. And I can show that by plotting it. So we are going to start plotting this. So we're just going to start off with figure equals make subplots, and then fig dot add underscore scatter, and our x values are going to equal, we're going to call it tplot, and we're going to define that up here. Tplot, and we're just going to make linear space values using numpy linspace, and we will start from 0 and go to 10 and make 500 linear space values in between there. And the y values will be the solution for the height at these t-plot values. So how we're going to do that is we're going to use our solve IVP function, which is giving us those answers. We're going to call it RES. And then our y values will be the RES solutions at our t-plot values. And again, this will be an array, the first index. So if we plot this, we get this graph here. And as you can see, our plot decreases, 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 then levels out here. And that right there is where our numbers are going negative and we start using the absolute value. And what we want on our plot is just this part here where it is positive. So how are we going to get it to stop the simulation right here where those numbers turn negative? And how we're going to do that is we're going to use an event, and that event is going to tell us when our numbers inside our square root here equals 0. And that'll be when it switches from positive to negative and we cut off our simulation. So now we can add in this event, and it is going to be a lot like how we added in this right-hand side equation. So I'm actually going to copy this. And now instead of calling this the right-hand side equation, we're going to call it when our v2, and again that's our everything inside this square root, is equal to 0 event. And again, we're going to be inputting t and y, and we still need this h equals y right there. But now all we need here is everything that is inside this square root. And we will be calling it v2. So we don't need these two. And we will need an event terminal v2 0 event terminal, and we want it to be true. And we have to return v2. And this should be v20 underscore event, and then I think it's dot terminal. Yep. So now we just need to put this event into our solve IVP function. So events will equal, and then we need to put our v20 event. And now finally, right here, instead of going from 0 to 10, we have to use the res.t underscore events command, and we have to put 2 indices here. And that should give us our final plot.